Hello, everyone, and welcome back to AI on AI. I'm thrilled about today's topic, that fascinating world of LLM reasoning. We've got 5 experts here to break down inference scaling, learning to reason, and agentic systems. Let's jump right in.
Thanks for having us. I'll start by saying the momentum behind improving LLM reasoning seems unstoppable. Every week I see a new technique or approach, like self-consistency or chain of thought, popping up. It's kind of like discovering a new gear in a race car you've been driving for years.
Ha, expert one, that's a good analogy. But from a business perspective, it doesn't matter how many gears you have if you can't steer the darn thing. One of the big strategic challenges right now is figuring out how to safely deploy these advanced reasoning models in real products. The complexity is just enormous. Cost, reliability, brand reputation, you name it.
Exactly. The complexity is definitely huge, especially when we talk about inference scaling, where we expand the test time computation. So for instance, we do iterative sampling, reflection, or even tree-based searches like Tree of Thoughts. Technically, it's powerful, but cost-wise, wow, it can blow through the budget if you're not careful.
Right? And from a technical angle, we often see methods like Monte Carlo tree search, MCTS, layered on top of chain of thought, especially for math or code tasks. That's extremely resource intensive. You have to keep in mind that each pass calls your large language model, which itself is pricey. On the flip side, if you're solving million-dollar problems, like certain legal or financial tasks, maybe that cost is justified.
Yeah, well, we had a manufacturing partner who used a multi-round search approach for scheduling thousands of assembly lines. They basically scaled up the inference like crazy. The result was a 10% increase in scheduling efficiency, which was huge for them. But they later realized the cost was ballooning, so they had to pivot to a partial learning to reason approach instead.
That's interesting. Could you unpack that partial learning to reason approach?
Absolutely. Instead of relying purely on a big LLM to do repeated inference calls, they decided to train a smaller specialized model, using a technique somewhat like offline reinforcement learning. They collected thousands of these scheduling trajectories, both successes and failures, and then taught the smaller model to emulate the best solutions. This drastically cut their inference cost. They still do some inference time branching, but nowhere near the scale they did before.
That's reminiscent of the shift we've seen from purely inference-based systems to actual learning to reason. DeepSeek R1, for instance, famously trained a reasoner with RL from correct answers alone, didn't rely on step-by-step ground truths. It's basically a big demonstration that RL plus a handful of well-labeled final outcomes can produce surprisingly sophisticated internal reasoning behaviors.
I remember reading about that. The emergent stuff, like reflection and backtracking, just sprouted up. Reminds me of that old Einstein quote, "Imagination is more important than knowledge." The model just imagines multiple routes and stumbles into correct solutions. And from a commercial perspective, that's a big deal. You could instruct a model to explore different solutions to complex contract negotiations. Imagine your legal bot charting all possible angles, learning at training time, so your actual inference is simpler.
Right. And if we look at agentic systems, that's a different but complementary approach. Single agent or multi-agent frameworks can call external tools or knowledge bases. Instead of generating all the text internally, they pass the environment. We've tried hooking an LLM-based agent up to code interpreters for data analytics tasks. It was like giving your AI partner a Swiss Army knife, opening up so many new capabilities.
We had a real estate client who gave a single agent system the ability to query property databases, fill out forms, and check local zoning laws. The agent saved them an entire full-time analyst. That's a prime business application. It's not just about dabbling in fancy algorithms. It's direct ROI, though obviously we had to ensure compliance and minimal hallucinations.
Right, that's the trick with agentic systems. If your agent starts hallucinating or taking unwanted actions, that's a real liability. So you often see generator-evaluator patterns. The agent generates a plan, a separate verifier or reward model checks the plan. Or in multi-agent setups, you get these debates among different LLMs. Some people even chain multiple role-playing LLMs to achieve better correctness.
Building on that, the debate pattern can be effective, but it also highlights a big question. Can we trust a chain of thought or a multi-agent conversation if each participant might still be incomplete? And to your point about cost, well, deploying 4 or 5 LLMs to talk to each other is not cheap. We've found it's better to do a bit of training to unify that process rather than run 5 massive models at inference.
Let me be the contrarian here. I think the entire multi-agent hype might be skipping an essential step. Everyone's trying to orchestrate multiple specialized LLMs. But if you can train one robust LLM to do the entire pipeline, you sidestep coordination overhead. Now, that might be technically more challenging, but from an operational standpoint, it can be simpler in many use cases.
That's fair, but not always feasible, especially if you need real-time external knowledge. For instance, if you're dealing with an inventory system or a live flight schedule, you absolutely need the model to query external data. A single monolithic LLM, no matter how large, can't store and update real-time states in its parameters. So agentic behavior, where at least the LLM can call external tools, becomes critical.
Great points. Let's pivot slightly into the business side. If you're a CEO or CTO thinking about adopting these advanced reasoning workflows, what are the watch-outs? Where do you start?
I'd say start small. Do a pilot. Evaluate if you need full inference scaling or if you can train a specialized reasoner. Also, factor in how often you need external verification, because that can transform your entire cost model. Another pro tip, always measure correctness or ROI carefully. If your agentic system is retrieving the wrong data, that's a fiasco waiting to happen.
Especially watch out for interpretability. If your system is fully reliant on chain-of-thought explanations, you might present all these intermediate steps to your business stakeholders. But, well, they might not mean much if your model is imitating reasoning rather than truly explaining. So keep that in mind. Transparency is crucial, but it must be meaningful.
We can't forget domain-specific reasoning either. For code, you can do test executions. For math, you can do symbolic checks. But for legal or creative tasks, it's trickier. We see folks designing specialized reward models or verifiers, like outcome reward models for final correctness, or process reward models for each reasoning step. But building and maintaining those can be a project in itself.
Then there's the question of data. We always talk about collecting high-quality reasoning trajectories. That might mean labeling each step in a chain of thought. Yet we found that unsupervised or automatically generated process labels might suffice. A retail company we worked with overcame their data bottleneck by auto-labeling simpler tasks and letting RL figure out the rest. They ended up with a partial process supervision pipeline that performed just as well as their earlier fully supervised approach at a fraction of the data cost.
That's a prime 80-20 rule scenario. You get 80% of the benefit from 20% of the labeling effort. The other big benefit with partial supervision is that it's more flexible. You can swap in a better reward model later if you discover your old one wasn't accurate enough.
Fascinating. On a lighter note, Expert 3, you mentioned agent-to-agent debate. Isn't that sort of like a boardroom full of consultants, each with their own opinions, passing the buck back and forth?
Ha, exactly. Sometimes it feels like an SNL sketch. Everyone's talking over each other, and you're not sure who's right. But if done properly, it can emulate the idea that 2 heads are better than 1, or 4, or 5, just as we get synergy in a real board meeting.
I love that image. But yes, in practice you need a well-defined communication protocol, like specifying how they share partial solutions. Otherwise, you get a tornado of text. In multi-agent frameworks, we often see adjacency constraints or role hierarchies to keep the conversation coherent.
Let me add a quick real example. We tested a multi-agent system in finance, using broker agents to propose trades, analyst agents to evaluate them, and risk agents to check for compliance. It performed brilliantly in backtesting, but once it ran live data queries, we realized we needed on-the-fly retrieval to handle late-breaking market updates. That forced us to do a bit of online RL for dynamic adaptation.
Right, and that's precisely the bigger strategic picture. Agentic systems are great if your environment is dynamic. For stable tasks, maybe a single well-trained LLM is okay. Also, from a leadership angle, I'd remind everyone that you must have fallback policies, like a human in the loop, and clear accountability. Don't just unleash an agent to do trades unmonitored.
So, to get more tactical, how do we do inference-aware training, as some call it, so that the model knows it can do more at test time?
One way is to include best-of-n sampling in the training objective. Another is to train the model with step-level exploration in mind. So if we know we're going to do a branching search, we normalize the training distribution to encourage more varied solutions. Or you can do preference optimization like DPO, but incorporate the knowledge that you'll only show the final best sample.
Precisely. Some folks have used something akin to a look-ahead reward shaping. The model gets partial credit for plausible partial steps, but huge credit only if the final is correct. It's reminiscent of playing chess with a few moves open. You have to plan for possible branches. It helps the model adapt better to inference time expansions.
And it all ties back to cost. The more we can train for inference time scaling, or train for better correctness, the fewer repeated calls we'll need. So it's a balancing act. But done well, it's a big leap forward. The brand new domain-specific reasoners or multi-agent solutions can drastically outperform older chain-of-thought or single-step models.
That's a great wrap-up. Before we sign off, any final words of wisdom on LLM reasoning? Maybe a final witty analogy?
I'll jump in. LLM reasoning is like rebuilding an airplane engine while you're in flight. You can't just stop the plane, do the updates, and then resume. You have to keep everything stable while pushing the boundaries of performance. So plan carefully, especially if big budgets and big risks are involved.
And I'd say stay humble. If the model seems too good to be true, test it more. Because, well, these AI illusions can be strong, and you'll want robust checks or a fallback strategy.
Words to live by. Thank you all. This has been a riveting discussion on inference scaling, learning to reason, and agentic systems. Our dear listeners, I hope you've gleaned practical tips, be it on the tech side or the business side. Until next time, keep innovating and keep questioning. Thanks for tuning in. Well, everyone, it looks like we have a bit more time than expected, so let's pivot into part 2 of our deep dive on LLM reasoning. I want to unpack some specifics on implementation and also uncover a few meaty business applications. Ready?
Definitely. Let's start with a nuts and bolts example. Suppose we're building a single agent system that integrates Python for code execution. Implementation-wise, you need a place to store the agent's working memory so it can pass partial computations to Python, read the results, and keep reasoning. It means hooking up an environment loop, like a micro-REPL, that's invoked whenever the LLM calls a run code function.
Yes, we did something very similar for a logistics firm. Their system had to run custom Python scripts for route optimization. Under the hood, we used something akin to a generator-critic structure. The LLM proposed a solution, the code environment offered a success or fail label, and we combined that to refine subsequent proposals. Performance soared by about 12% in route efficiency, rewriting our internal route cost heuristics. The key is robust integration with the environment loop, so the agent can call external code precisely when needed.
Strategically, that's huge for enterprises. They can tailor the step-by-step code calls to match their existing software processes. But as a business leader, you better ensure your data flows are bulletproof. No random overwrites, no security lapses. The last thing you want is an LLM calling your production cluster in ways that break everything.
Right. You can't just whisper "run code now" and cross your fingers, especially if that code touches financial data or personal info. Proper sandboxing is essential. On the technical side, I've seen system architects register each function or tool with an official schema. The agent sees a function name plus parameters like retrieve inventory, stock ID 1234. Then the system checks if that's a valid function call before executing. So it's not just freewheeling text out there.
This is where the MDP formalism, or Markov decision process, can come in. You treat each function call as an action, and every environment state includes relevant logs or memory. Then, if you add a reward model, like a success-failure measure for these function calls, you can do step-level RL. That's how DeepSeek Prover and others systematically improve their proof strategies.
Great. That's a solid technical blueprint. Let's shift to another angle, multi-agent setups. How do we actually implement the communication patterns so that the agents, they aren't just babbling?
Indeed, babbling agents can happen. One popular method is a round-robin style, where each agent posts a short message to a shared message board. Another approach is star topology. A central planner agent or dispatcher receives partial outputs from each specialized agent, merges or critiques them, and circulates a refined state. All you do is define, at the code level, how many conversation turns each agent can have and which messages they can view.
Right. One tip we discovered is forcibly limiting each agent's token budget in a single turn. If you allow unlimited text, they can produce essays that nobody else reads. If you keep each turn concise, you manage cost and also maintain clarity. So for a multi-agent conversation, you might do no more than 3 or 4 cycles total, especially for time-sensitive tasks.
That's reminiscent of the debate pattern, but we tested a collaborative pattern for an insurance giant. We had a policy agent that documented constraints, a legal agent that flagged compliance issues, and a finance agent that worked out cost estimates. The central aggregator then combined their partial responses. Implementation required a simple conversation buffer, like a chat record, plus a directive ensuring each agent only touched specific segments. It ended up saving stakeholders around 15% in processing time for complex claims. From the business perspective, that's a big deal. Speed plus accuracy in insurance claims is a differentiator. You just have to weigh that improvement against the engineering overhead. Each new role or agent might mean new data structures, new error checks, and of course, new language model expenses. So always measure ROI carefully before spinning up an 8-agent extravaganza.
Love it. Now, what about training these agent setups? We've mentioned preference learning, direct preference optimization, and so on. Where does that fit with the multi-agent world?
Typically, you can unify them under the multi-agent synergy approach. You log all the messages from successful or partially successful runs, meaning the final environment outcome is correct, or the final tool usage passes. Then you do an offline training of each agent's policy to replicate those trajectories. Some add a critic model that scores how well the group did. So for each agent's partial action, you can measure synergy. Then you do multi-agent PPO or a version of DPO.
Let me add a contrarian twist, though. Multi-agent RL can be complicated to scale, since each agent's updates can affect the others. We see cyclical or chaotic training if you're not careful. So in practice, a simpler approach is to freeze certain roles and train just one variable agent. Or do a staged approach. Fix your aggregator agent, then refine your specialized ones. That can be more stable.
We tried exactly that at a crypto exchange. They had maker agent, taker agent, risk agent, and settlement agent. We first toyed with full multi-agent RL, disaster. The system kept oscillating. Then we froze risk agent plus settlement agent and only trained the maker and taker. That stabilized performance. Net result, more robust trades, fewer weird feedback loops.
Good to know. Let's pivot to real-world business use cases. We've heard a few. Maybe we can highlight a couple more.
Sure. We helped a telecom company tackling dynamic pricing. They have an LLM-based reasoner that can see competitor data from a web scraper, analyze it for new promotions, then generate potential price adjustments. A mini verifier agent checks if the new prices violate margin constraints. They slash staff time by 30%. The LLM system proposes decently optimized pricing daily. That is tangible ROI. That's huge. And ironically, the simplest part was the aggregator. They already had internal APIs, so hooking in external knowledge was straightforward. The hardest part? Convincing their finance department that a language model could be trusted. So they did months of pilot tests against historical data. That business readiness piece is always bigger than it looks.
Another interesting domain is biotech. We worked with a lab that used reasoning LLMs to propose gene editing experiments. The environment is a simulation platform. The LLM tries out new CRISPR plasmid designs via a coded interface. Over time, it got quite adept at eliminating unviable ones, saving, probably thousands of dollars in wet lab tests. So that's a big cost avoidance angle.
Yes, that's one reason domain-specific reasoners are on the rise. If you're tackling biotech or advanced manufacturing, you can't rely on general knowledge alone. You often train or fine-tune a specialized model, plus possibly a domain reward model, like we do for math or coding. Then inference-time expansions, like searching multiple plasmid designs, are done selectively, not for every step.
That's fantastic. Let's also inject some humor. Expert 5, earlier you said your system was, like a bunch of unstoppable interns?
Ha, yes, unstoppable interns with infinite coffee and a big imagination. They can keep churning out partial solutions without sleeping, but if you don't supervise them, they'll come up with the weirdest ideas. That's basically LLM reasoning in a nutshell.
Just be sure to give them a budget. Infinite coffee is expensive.
Indeed. Great. Could we do a final technical deep dive on process reward modeling? That's come up a few times.
Sure. In process reward modeling, you label each step in a chain of thought as correct or incorrect. That yields a step-level reward signal. The architecture is typically a separate classification or scoring model, like a PRM, process reward model. The LLM reasoner then gets partial rewards after each step. Implementation-wise, you keep a table. Step T, state ST, action at, reward. Then you do a normal RL update like PPO or even simpler methods like RLOO. The main challenge is data. You either label steps by hand or do clever rollouts with a known answer, like code test cases or math solutions.
Right. If you have a big library of correct solutions, you can roll out from partial steps, see if it leads to the correct final answer, and label them correct so far. But that's computationally heavy. So many folks do approximate labeling or noise-robust learning. It's definitely not trivial, but it can help the model learn intermediate correctness clues, so you end up with fewer random leaps.
We use that approach in a compliance scenario, labeling partial text as safe or borderline. The step-level reward model was effectively a compliance classifier. If the chain of thought contained disallowed topics, we gave negative feedback. Over time, the system learned to correct itself mid-reason, drastically reducing risky utterances. That's a prime compliance use case for process reward modeling.
Wow, that's thorough. Time's almost up, so last-minute thoughts?
My main takeaway: whether you do inference scaling or training time specialization, always incorporate some form of cost monitoring and interpretability measure. No free lunches in this domain, especially once you move from sandbox to production.
I'll just say keep an open mind on the synergy between new architectures and new training regimes. Don't get locked into old patterns. LLM reasoning is evolving so fast, we might be rewriting best practices every quarter.
Perfect. This has been a phenomenal part 2, digging deeper into the how-to and the real-world why. Thanks to all 5 of you for sharing your expertise, the unstoppable interns, the comedic disclaimers, everything in between. On behalf of AI on AI, thanks for listening, and see you next time for more frontier discussions. All right, everyone, before we officially sign off, I'd love to do a quick recap, highlight the journey we've taken over these discussions, and pinpoint the key innovations and insights we've uncovered.
Sure thing. If I had to summarize, we covered how LLM reasoning breaks into 2 main paradigms: scaling up inference through techniques like tree of thought searching versus training time methods like preference learning or RL. And the interplay between them, that's where we see the next frontier: inference-aware training, ensuring that what we do at test time actually informs how we train.
Absolutely. We also touched on how agent architectures, be they single agent or multi-agent, can give us more interactive loops. For business leaders, that can be a powerful blueprint. You can pick the simplest system with a standalone model if that suffices, or go for multi-agent synergy if you need specialized roles. That architectural choice is critical for ROI.
We dove deep into process supervision and how that combats hallucinations by rewarding correct intermediate steps. That's a big departure from older, outcome-only approaches, and it's a major innovation. If you want to minimize the risk of meandering, employing a process reward model or a generative verifier can be a game changer.
Right. And from a purely technical standpoint, the Markov decision process framing is super important for implementing RL. Defining states and actions carefully, whether every token is an action or each entire solution is one big action, really shapes the outcomes. This is not just an academic point. It's the core of making agents that handle tasks in finance, insurance, or biotech safely and effectively.
And let's not forget the real-world results. We saw how a logistics firm boosted route efficiency, how an insurance team sped up claims, how a telecom optimized pricing, and how a biotech lab cut experimental costs. These are prime examples of how well-implemented LLM reasoning can translate directly into competitive advantages.
That's fantastic. For me, the key insight is that building a reasoning system is not just about bigger models, but smarter synergy across inference strategies, training data, and system design. We've heard about domain adaptation, cost monitoring, security, and the emerging best practices. Any final words?
Just that this field is evolving lightning fast, and many of the best ideas come from bridging business needs with advanced techniques. We'll likely see new paradigms soon, like truly proactive agentic systems or partially symbolic hybrids.
Indeed. As Einstein said, imagination is more important than knowledge. With these LLMs, we're unleashing imagination, but we still have to guide and fine-tune it responsibly.
I love it. Thanks, everyone, for such a thorough exploration. This wraps up our multi-part series on LLM reasoning. We hope our listeners gained a crystal clear view on not just the theory and tech, but the strategic angles too. Until next time, this is AI on AI, signing off.